This is a joint work with Anurag Anshu and Nicholas Breukman. I will start by defining circuit to Hamiltonian mappings. The goal in these mappings is that given a circuit, we want to derive a local Hamiltonian such that we can easily extract computation output from its ground state. And this is a fundamental tool in TCS and quantum information. It provides many interesting connections between complexity theory and many-body physics. So classically, we can do this by the Cook-Levin mapping. In this mapping, we place a bit on each wire in the circuit, and the Cook-Levin Hamiltonian is a poly-Z Hamiltonian, such that the ground state is a bit string that is the concatenation of the intermediate states of the computation. Quantumly, we cannot do this Cook-Levin style history state because of the local indistinguishability of quantum states. Instead, we use the Feynman-Kitaev history state, where now instead of laying out the computation as a tensor product of the intermediate state, we put them in a superposition. And this is done by introducing a clock register. And this clock register partitions the Hilbert space into a direct sum, and the intermediate states are put into each component in the direct sum. This history state is the unique ground state of the Feynman-Kitaev Hamiltonian. The input Hamiltonian term looks at the first component in the direct sum, and it wants to see the all-zero state. The propagation terms look in between adjacent components in the direct sum, and it wants to see that the gate is applied in going from time step t to time step t plus 1. The motivation for our work is the observation that the Feynman-Kitaev mapping lacks a robustness property of the Cook-Levin mapping. And we expect that this property could be useful to approach the quantum PCP conjecture via a connection with fault-tolerant computation. We make progress in obtaining a new quantum circuit to Hamiltonian mapping with this property. And as a result, we also give a new proof of the QMA completeness of the log local Hamiltonian problem. So what is this robustness property? The property is that unsatisfying bit strings of the Cook-Levin Hamiltonian still encode a noisy version of the computation. So as an example, if we have a bit string X that satisfy all terms except 1 in the Cook-Levin Hamiltonian, then this bit string still encodes the noisy computation with the one faulty gate. This is not true in the Feynman-Kitaev mapping. And we can easily come up with state such that it, like this one, such that it violates exactly one term in the Cook-Levin mapping, and it contains no information about the computation. In this example, this state is just the all-zero state in the first block, and it has no components in the other block, and it only violates the first term in the propagation Hamiltonian. So now I'll describe our construction. I'll do this in 3 steps, and the first step is to encode the quantum circuit into a simple product state, which is the all-zero state tensor product with the choice states of the gates in the circuit. In this talk, I'll assume the gates are 2 qubits, so the choice states are 4 qubits. This state is clearly a unique ground state of a simple 4-local Hamiltonian, and seemingly this gives us a mapping from a quantum circuit to Hamiltonian. The issue is that we cannot easily extract the computation output from this state. However, we can learn something from this mapping by intentionally arranging the components of this product state to be aligned with the architecture of the circuit. And here we denote the choice state using the tensor network notation. So in some sense, it looks like what we need to do is to make the choice state talk to each other and make them do the computation for us. This is what happens in step 2. And the idea is that we can implement the gate using the choice state and the projector, the EPR projector P. What we do is we say if we want to apply a gate U on a state 0, what we'll do is we can hit the first 2 qubits by the projector P, and as a result, we'll get the U applied on 0 on the third qubit as desired. This can be generalized to a general circuit. So we will have the all zero, a tensor representing the all zero input state. We have tensor representing the choice states, and then we hit the adjacent legs of the adjacent tensors by the projector P. This gives us the output of the computation on the rightmost column of this tensor. So this is a tensor network known as PEPS. And now we do have the computation output in this state. The issue is that this PEP state is no longer the unique ground state of a local Hamiltonian. So the step 3 is to reconcile the first 2 steps. We want to get a local Hamiltonian and such that the ground state is such that the ground state encodes the computation output. And we do this by considering a variant of PEPs called injective PEPs. So what we do is that we replace the projector P by some invertible map Q that I'll specify shortly. And this gives rise to the so-called injective PEP state. This is a standard fact that this injective PEP is a unique ground state of the so-called parent Hamiltonian. This parent Hamiltonian is just the original Hamiltonian for the product state in step 1, but now it is conjugated by the inverse of Q. So this is where we need the invertibility of Q. And what Q do we choose? So we saw that in step 2, the projector P gives us exactly the computation. So the natural choice is to choose Q to be a little of perturbation from P. So this is the choice that we make in our work. So the question is, what does the ground state look like for this perturbation of P? So the main observation is that before the projector P performs a perfect gate, as we saw in step 2, but now with the Q being a perturbation of P, it turns out that it performs a noisy version of the gate under depolarizing noise of strength delta, which is the strength of the perturbation in Q. So for a general circuit, we can show that the ground state of this parent Hamiltonian encodes the computation with local depolarizing noise per gate. The last thing we need to do is to replace the circuit by the fault-tolerant version of it, and this will handle the noise. So in summary, we have a Hamiltonian from a tensor network. The ground state is an injective PEP state. The rightmost column contains the output with depolarizing noise per gate, and we use the fault-tolerant version of the circuit. So we can give a new proof of the QMA completeness of log local Hamiltonian using our construction. And the main lemma that we prove is that the spectral gap of the Hamiltonian is exponential in the depth over times 1 over poly n. So this spectral gap is quite bad compared to the Feynman-Kitab spectral gap, but the main observation is that QMA circuit can be assumed to be log depth. And so what we need to do is we constructed a fault-tolerant version of the QMA circuit while maintaining the depth of log n. We couldn't do this with 2-qubit gates. We used a few layers of log local gates, and it turns out that this is enough to give a 1 over poly spectral gap, and this gives us the proof of QMA completeness for log local Hamiltonians. And the fault-tolerant construction is based on recent families of linear distance quantum LTPC code with so-called local parallel decoder. Next, I'll talk about the properties of the tensor network Hamiltonian beyond the ground state. And this is where we think that it could be useful for quantum PCP. first need to give some definitions. So epsilon energy states mean the states that have energy density epsilon with respect to the Hamiltonian. Alpha combinatorial state is a special case of epsilon energy state in which it either if it either violates one term or it completely satisfies the term. And one can show that epsilon combinatorial is a special case of epsilon energy. And the reason we define this combinatorial states is because there's some statement that we can only prove with combinatorial states. The third definition is about computation. A kappa adversarial computation is a computation in which in each layer of the circuit, at most a kappa fraction of gates are faulty. Our main soundness result is that the excited states of the tensor network Hamiltonian still encode noisy computation. In particular, we prove that 1 over poly D combinatorial states encode 1 over poly log adversarial computation. And exponential in-depth energy states encode 1 over poly log adversarial computation. So these the quantifiers only depend on the circuit depth but not the circuit size. And these are the semi-classical and quantum analogs of the Cook-Levin robustness property that I mentioned in the earlier slide. And so as you can see, the exponential in-depth quantifier in the property 2 is much worse than the 1 over poly depth in combinatorial states. And we actually believe that property 2 should also hold for 1 over poly energy state. And this is an open question. So why do we want to have this kind of statements? The goal is we want here is to have some soundness analysis beyond the spectral gap. So conventionally, the soundness analysis in the Feynman-Kitab mappings use the 1 over poly n spectral gap of it, and there are no guarantees known above the spectral gap of the Feynman-Kitab Hamiltonian. So for example, in Kitab's proof, he used the spectral gap to prove QMA completeness. This is also what we did that I described in the earlier slides. But here, as we saw earlier, the spectral gap of our Hamiltonian is exponential in depth. However, from the properties that we saw in the previous slide, 1 over poly D combinatorial states, and yet the property 1 that we saw in the previous slide still asserts that they stay close to the computation in the sense of kappa adversarial computation that I defined earlier. And we think such robustness encoding of computation into excited states could be useful for quantum PCP. So just a reminder, quantum PCP asks that we know that inverse polynomial promise gap of the local Hamiltonian problem is QMA hard, and quantum PCP is about, it says that it's still QMA hard for when the promise gap is constant. And for this work, we think that our Hamiltonian could be useful for the polylog version of quantum PCP, in which the promise gap is 1 over polylog. And the reason is because there is a connection between classical polylog PCP and adversarial fault tolerance. This was first observed by Gao and Zagady in '96, where they observed that the Cook-Levin mapping gives a classical version of property 1. 1 over poly D combinatorial states of the Cook-Levin Hamiltonian encode 1 over polylog adversarial computation. And using the fact that NP circuit can be assumed to be log depth, we can combine this Cook-Levin robustness property and an adversarial fault tolerance scheme to prove polylog PCP. So the goal that we still fall short of achieving in our work is to establish a quantum version of this polylog PCP adversarial fault tolerance connection. The main open question is to prove property 2 for 1 over poly D energy states. And recall that if that is the case, and recall that QMA circuit can be assumed to be log depth, then a quantum fault tolerance scheme for 1 over polylog adversarial computation would imply polylog quantum PCP. So currently, we only have the 1 over poly D the same statement for one over poly combinatorial states. So currently what we have is like a combinatorial version of the statement. I'll conclude here. Thank you for listening.